graph, and more exactly about the construction in subquadratic times. So it's a joint work that I made with Eric Rivals, which are in the lien with me, and with Kunsoo Park and his student, Gwan Park, which are in the Seoul National University. So just the outline. So at the beginning, I speak about why we want to use this hierarchical overlap graph. And after that, I speak about the main algorithm and how we can improve this algorithm by using the segment tree. Okay. So thanks, Sebastian. Just before to make me the introduction about the genome sequencing. So but just the idea is in practice, when you want to make genome sequencing and genome assembly, we need to use some type of overlap graph. So we have two big type of graph, which are overlap graph and De Bruijn graph. So Sebastian speak about De Bruijn graph, and here I speak about overlap graph. So what is overlap graph? So this is an example. So overlap graph is a weighted complete graph where the node is the set of widths that you have at the beginning, and a weight. I don't know. I think you see my mouse. So a weight, for example, here is 4 between U, this width, and V, correspond to the longest overlap. So the longest overlap. An overlap is a suffix of the first width, which are also a prefix of the second width. So here we have AACG, which are in the prefix here, and AACG is a suffix here. So it's an overlap. It's a maximal overlap here. So it's a weight in the overlap graph. But the problem that when we want, okay, I could read. So, but in theory, in assembly theory, we have a problem, a theoretical problem, which corresponds to, for a set of string P, we want to find the shortest superstring problem, which corresponds to the shortest string that contains all the string of P as substring. And we know that this problem is equivalent to finding a maximal weight Hamilton path in the overlap graph. So, for example, if we take the same example as before, so P is this set of strings, and on the left, on the top of the left, we see the superstring, and we see the string of P, which are substring of the superstring, and this superstring corresponds with of the path in the overlap, which correspond to CACG. After that, we see AACGTA, and after that, GTACAA. Okay, so now if we can build the overlap graph and we find a path of maximum weight, we can obtain the shortest superstring. But one of problem is, as is a complete graph, the length of the overlap graph is quadratic in the number of widths that you have, which can be really more in practice. So to have a linear algorithm, in the last paper we presented the hierarchical overlap graph. So what is that? It's a sort of data structure. In fact, is embedded in a data structure where the node are the set of strings of the set of strings what you have at the beginning, and the maximal overlap between the strings. And for the arc, we see two different type of arc. Here it's the black and the red. The black here, we add a black arc between U and V if U is the maximal proper prefix of V in all the node. So here, for example, for AACD, the longest prefix is AA. And the red arc from U to V go from a string to the longest proper suffix. So here is CD. And this structure of suffix relation and prefix relation, we define the HOG, or hierarchical overlap graph. So this is an example. But in fact, in practice, in the last article, we don't arrive to find a linear algorithm for this graph. So we defined almost overlap graph, hierarchical overlap graph, which calls the extended hierarchical overlap graph, or EOG. And just we modify the set of nodes, and instead of taking just maximal overlap, we take all the overlap between strings. And now it's more easy to compute because you can compute it in linear time. I explain after how we can do it. But the problem that the EOG can use considerably more space than the HOG. For example, here, the node U2 is in the EOG, but not in the HOG. Okay. Why it is useful to compute the hierarchical overlap graph? The first thing is in space is less space than the overlap graph. So here I mentioned that the space of the overlap graph is the norm of P plus n square, where n is the cardinality of P, and the norm of P corresponds to the sum of the length of the strings in P. But in fact, you can say that you can remove the norm of P because you don't need that. So it's in n square. But the size of the HOG is on norm of P. But we can also prove that the size of the HOG is also in big O of n square. So the size of the space of the HOG is less than the overlap graph. And also we have more information than the overlap graph because in the HOG we know if two strings or four strings, a pair of two strings, correspond to the same overlap that we don't know in the overlap graph. And also it's useful for that is useful in shorter superstring problem, but I just mentioned that, but here it's just about the construction of the hierarchical overlap graph. Okay, so we proved before that in fact you can build the HOG, so the extended version of the hierarchical overlap graph in linear time and space in the norm of P. So this is really easy by using the Arocorasic tree, for example. But in the last article, we give a norm of P plus n square algorithm in time to compute the HOG, and the space is this guy. Okay, but in fact, you can see that if all the string of P have the same length, in fact, this guys comes. It's in big O of norm de P. So where the P have strings of the same length, it's okay for the space complexity. But in the case where one string of P are bigger than the other, the space comes norm de P plus n square, which is not really good. So here we present a different algorithm to compute the HOG, which are linear in space, but which are norm of P times log n or log n over log n in time. Okay, so to present that, I just need to define two set of overlap: the of plus, which correspond to the set of all overlap of string of P, and of P, which are just the maximal overlap between the pair of weights of P. And now, in fact, compute the HOG for us as we can compute the extended hierarchical overlap graph in norm of P, in fact, we need just to, the point is just to how we can compute the set of the P. So the set of all the maximal overlap of P. Because if we know which node of the hierarchical overlap graph, extended hierarchical overlap graph, so EOG of P, are in of P, we can compute in linear time the HOG. Okay. So that it's just to understand how it's how you can compute the HOG from the Hierarchical tree, because in fact EOG, the extended hierarchical overlap graph, is embedded in the Hierarchical tree. So, for example, here, if we remove this node, which are not in the EOG because that doesn't correspond to the overlap, if we remove it and you merge the arc, you obtain the EOG. And now, if you remove, you keep only the node which are in of the P and not in of plus the P. So, for example, U2 is not a good overlap because it corresponds to the overlap between AA, BAA here and AACD with A, just A, which are not the maximal overlap because you can take AA, so we want to remove it. So if we remove it, we obtain the HOG here. Okay. So, and in fact, it's for that we know that the number of nodes of the HOG and the EHOG, as it's embedded, the both are embedded in the Hierarchical tree, we know that the number of nodes are less than the norm of P. Okay, so now how we can build it? What is the main algorithm? So the idea here is really easy. In fact, we compute the Hierarchical tree of P. After that, we remember the string in lexicographic order. So, for example, here we have 1, 2, 3 because AABAA is lexicography smaller than AACD. Okay, so it's like that. And after that, we compute the EOG in norm of P. And after that, for each node, in fact, we can compute the interval, the EU set, which are here, which correspond to the interval of the leaf which are in the subtree when we see the black arc. So, for example, here, if I take the U1, the interval of the leaves, the interval of leaves which are in the subtree of E1 is 1, 2, 3. But for U2, it's just 1, 2, and for U5, it's just 3. And now, we will compute of the P from the EOG. So, in fact, we need to have a good property to find which nodes are in of the P, but and which nodes are not in of the P. To understand that, we see that, in fact, what is an overlap? An overlap is if U is an overlap of SE to SJ, SI to SG, U, in fact, is a proper suffix of SG and is a proper prefix of SG. And if it's the longest overlap, we know that we don't have an overlap which are bigger. So the idea is we compute for all the leaf. We see the failure link chain. So in fact, I explain after that better, but I try to explain just before now, and after that with an example. But the idea is for each leaf, we can go until the root by taking failure link chain. So in fact, we take a leaf, and after that we see the proper suffix, the proper longer suffix of this leaf, and after that you continue, and you arrive to the root. And when you make that, you see suffix after suffix, longer suffix after shorter and shorter suffix. And when you make that, you can check the interval value of the subtree of leaf and update if this pair have already seen or not. And to maintain, to store this information, we use a bit vector of length n. So the n corresponds to the number of leaf. So we have one position by leaf, and we say that BG is true if when we see this node, this element have already been seen before. Okay. So I explain in an example. Maybe it's more easy. So and we make that for each leaf. So for example, for the leaf 1. We follow the suffix link until the root. So we start from 1. After that, we go in U4, U2, and we stop in U1. So in 1, we use BG, and B, the length is of size 3 because it's the number of leaves that you have. And B, store, just remember that the store, if it's possible if we have already an overlap, a maximal overlap between from 1 to G. So to 1, to 2, or to 3. And so when you compute, for example, if we have in U4, the interval is 1 and 2. So now we can check in BG if B1 and B2 is false. If it's false, you know that A4 is the longest overlap between S1 and S1 and S1 and S2. So now you know that in the HOG you need to keep it. So you keep it, and you update the BG value for 1 and 2 to true. And you continue for U2. For U2, the interval is exactly the same, 1 and 2. But when you see in BG, these two values are already be true. So we don't need to add it. So we don't add it, and we continue to U1. And to U1, now you have 3, and 3 is false when you write. So now you need to add it, because you need to add U1 because it corresponds of maximal overlap between 1 and 3. And you continue, and you can make that for each leaf, and you obtain this marking node. And if we remove U2, so the only internal node which are not marked, you obtain the HOG. So this is the idea. And this is the main algorithm. So it's exactly what I presented. And if we see the algorithm, we make two different things in B. It corresponds to update. So if we have an interval, we need to update all the elements of the interval at true, and also a check. For an interval, we need to check if in the interval there exists an element which are false. So if we have these two query, so the check and the update, it's enough to make the main algorithm. And if we use just a bit vector, we can make this update thing in n, in big O of n. But now that to improve this thing, we store this bit vector B as a segment tree. So what is a segment tree? So okay, I go quick here because it's not really useful to have all the formal thing, but the idea of the segment tree, it's a tree which, for example, here it corresponds to the segment tree of the interval 1,6. And in fact, in this tree, we can store every segment of in every interval of 1/6. For example, if I want to store 1, 5, in fact, it corresponds to this both node 1, 3 and 4, 5. And over interval, for example, if I want to see 3, 4, I need to take this node and this node. And the particular thing of this segment tree that, in fact, we can update we can update and check in log n, in big O of log n, because log n is the 8 of the tree. So by using a segment tree, okay, I pass because it's just about how it's computed in segment tree, but it's just that we know, that we need to know. It's just that, in fact, for each query, you only need log n. And so, as for each query, we need just only log n, and the total number of elements that you need is norm of p. It's the number of queries that we need to do. At the end, the time complexity is norm of p of log n. And as the HOG and the segment tree cost norm of p of space, the space complexity at the end is norm of p. So at the end, we can compute the HOG in norm of p log n time and norm of p space. But if you modify the segment tree by using the world RAM model of log n, and the world size is log n, in fact, instead of for your segment tree for a node to have just two children, you can have log n children. And now is the query is in log n over log n, and now you have an algorithm in norm of p of n times log n over log n. Okay, and now just to mention it, in fact, in the open question, I add can one get a linear time algorithm? But in fact, yes, we can. With the Korean guys, we have presented in the last CPM, so it's this CPM, a linear implementation of the a linear algorithm of the HOG, and also other guys, which are Shabazz Khan, give also another algorithm to compute also the HOG in linear time, and he submit also in CPM. But the second question, which here can we extend this data structure to approximate overlaps? In fact, we don't know. I think it can be a previous question. Okay, thank you.
Thank you very much. So I'll start reading the only so far question that we have. Regarding lexicographic ordering, wouldn't it suffice to order leaves of any valid trie from left to right? The internal nodes would still correspond to an interval of the leaves.
Yeah, I don't understand exactly what's the question, but yeah, I think as it's you can ordering all the lexicographic order. You can order all the string in linear time. We make that. In fact, it's just. In fact, yes, I think we can make better, but yeah. So I think we can.
Okay, thank you very much.
You're welcome.
Are there any more questions? Okay. Just out of curiosity, any thought on the very recent preprint that proposes an optimal construction?
Okay, I just check which paper is it.
Okay,
yeah. It's one of the paper that I mentioned just at the end. It's the paper of Shabazz Khan. I think who asked the first question, and we have discussed a little both, and it's but I think we have already also an optimal construction. So yeah, So now we have 2 optimal constructions, so it's good.
Okay, thank you very much. Again.
Thank you.
So I'm introducing the next speaker, Manuel Cáceres.
Hello.
Okay. Hi, Manuel. Please share your screen. Manuel is going to give the talk titled Safety in Multi-Assembly by Path Appearing in all path covers of a DEG. Please go ahead.
Thank you. So my name is Manuel Cáceres. I am a PhD student from University of Helsinki. And today I will present you how to compute safe paths for path covers in directed acyclic graphs and applications of these to multi-assembly. This is a joint work with my supervisor, Alexandru Tomescu, and also joined with researchers and Professor Brenda Mumin, Entin Husik, Romeo Risi, Massimo Cairo, and Christopher Sacchi. But first, I would like to talk about puzzles. So many problems in bioinformatics can be seen as puzzles, where we have only the pieces, and the objective is to build the entire puzzle. So, for example, in genome assembly that we have discussed here extensively until now, we have reads of some hidden genome that we don't know, and we want to reconstruct this genome from these reads. Another example is the multi-assembly, which is some sort of generalization of the assembly problem, where instead of only one sequence, we have different sequences, and we have reads mixed from all these sequences, and from this mixed set of reads, we want to reconstruct all the input genomes. So coming back to puzzles, some puzzles are solved perfectly. We can obtain the solution to this puzzle. And in general, in computer science, in theoretical computer science, we define the problems to be solvable in theory. But in practice, we see that we encounter, for example, in bioinformatics, many unsolvable puzzles. And in bioinformatics, this happens a lot because there is not only one solution that solves the problem that we are interested in, but there are many solutions. So which one we choose? So first, what we propose is, as a general framework, we're going to output only things that are for sure part of the real solution. The first thing that we could say naively is that we're going to output the input itself, because that is part of the solution, a sub-part of the solution. But we could do better also and try to output a bigger sub-part of the solution that we know for sure that will appear in the real solution. And we call to this part safe, and we want them as big as possible. So this in genome assembly are exactly what contigs are. Contigs are subsequences of the original sequence that we want to record, that for sure we know are part of the genome. And there are a lot of practical assemblers now reporting contigs. And also there is a lot of work theoretically that is not only interested in safe solutions, but only incomplete. That this is how much we can report what is